Hey, welcome to the video for Math 2413, Calculus 1, for November 9th. And notice this is Dr. Holt, this is not Sal Khan, and that's because Sal's videos on this particular topic, I don't find them to be the best. So I've decided to make my own. And what we're going to do here is define a definite integral. So we've been dealing with indefinite integrals for a while, and that has basically just been a synonym for antiderivative, a backwards derivative. What does it mean when we make the integral definite? Well, I want to remind you of what a derivative is, and then we'll use that idea of what a derivative is to talk about what an integral is. The derivative of a function is equal to the rate of change of that function. Okay, now graphically we defined that as the slope of the tangent line, but that's really restrictive to only the graphical case. And in general, the derivative is just giving you the rate of change. And an integral is very similar in that we usually define it geometrically as the area under the curve. That's usually how we think of an integral. However, it turns out that in life applications, it's much, much more than that. And the reason that the integral is important is not just because of area, but because it allows us to compute an amount of change from a rate of change. So an integral of a rate of change gives us the amount of change. And this is going to be a definite integral rather than an indefinite integral. Okay, so I think we're due for an example here, and I'm new to this whole typing, and I'm also going to draw on the screen once I get to more math symbols, but if I try to write all this prose out, I think you would have a hard time reading it. And we're going to do two examples to introduce what this definite integral thing is, and we'll eventually get to area under the curve, but I don't want to start with that. First of all, I'm going to suppose that f prime of x is 3x squared plus 2. And I'll need to write later, so I'm going to go ahead and type and then I'll write that later. And what we're going to look at is how much does f change between x equal to 1 and x equal to 3. Okay, so let me get my pen working here. And I'll use white. So suppose f prime of x is equal to 3x squared plus 2. This is a rate of change, and what we're going to do is go from the rate of change to the amount of change. How much does the function change? Okay. Well, this actually isn't too hard. I can find a formula for f just by doing the integral, just the good old indefinite integral. And we have the integral of 3x squared plus 2 dx. That's my function. Now, it's a little bit ambiguous because we have this constant around. But we're going to find that when we're computing total change, that constant doesn't matter. Now, if I want the change in my function between x equals 1 and x equals 3, well, I can just find its values and subtract, right? So I would take f of 3 and subtract. No, I don't want to erase everything. I just want to erase a little bit here. And I'm going to subtract f of 1. And that will give me my change in f, which I'll write as delta f here. Alright. Well, I've got a formula for f. And that just gives me, let's see, 27 plus 6 plus c minus, and if I plug in 1, I get 1 plus 2 plus c. So this gives me 33 plus c minus 3 minus c. And notice our c's cancel, and we didn't even need to figure out what that constant was. And our total change is 30. And this is a definite integral, and we're going to write it like an integral. What we just did here was compute the integral from 1 to 3 of f prime of x, of 3x squared plus 2 dx. So this was our rate of change, and computing the definite integral gave us the total change of our function. Okay, I'm going to clear the screen here and we'll see if we can't do this other example. Well, I'll leave that top stuff there. So we'll do a second example now. And the second example is going to be a little bit less abstract. Suppose I ride my bike for 10 seconds. T seconds, no, I don't want that capitalized, Microsoft Word. Thank you for suggesting it anyway. T seconds after I start to ride my bike, my velocity is, and then I'm going to write down a formula. And what I want to ask is how far do I travel in those 10 seconds? And the formula for my velocity, let's see, I'm going to change to pen mode here. Uh-oh. Maybe I do need to erase all this. It's all my old stuff. The formula for velocity is going to be v of t is equal to negative t minus 5 squared plus 25, and that whole thing is going to be in feet per second. Okay, now I chose this function because it's a somewhat reasonable shape for our situation. Okay, I get out 0 when the square is 25, so when the inside is 5. And that happens when t is 0. I get minus 5 squared. It gives me a 25. Stick a negative on it, add a 25, and that's 0. Or when t is 10. That gives me 5 squared. 25, stick a negative on it, and add to 25 gives you 0. So this is at 0, and over here we have t equals 10. So I'm speeding up, speeding up, speeding up. And now I've peaked on my velocity. Here, my velocity is still positive, because this is a graph of velocity, not of distance. Okay, but I'm slowing down here. And what I want to do is work with my distance function, where d of t is going to be the distance. Actually, you know, a better way to put this, yeah, I'll call it distance traveled. Okay. Now we know how distance traveled and velocity are related. We know if we take the derivative of distance traveled, we get velocity, right? Because this is measured in feet, and then if I take the derivative, I get a rate of change, feet per second. So I know that d prime of t is v of t. And what that means is d of t is the integral of v of t dt. An integral is going backwards from a rate of change to give you the actual function that's changing. And a definite integral is going to give you the amount of change from that function. Well, I can take the antiderivative of this, and let's see, what do we get? We get d of t equals the integral of negative t minus 5 squared plus 25 dt, and I like to keep my integrand, is the name of the stuff that you're integrating. I like to keep my integrand in parentheses. Okay, and using, some people would want to use substitution, some people might just be able to pull this together. With this first term, I've got something squared, and that variable is in the base. So the power will increase by 1. I've got that negative hanging out there, and I get 1 over the new power. Okay, this term will end up giving me derivative of that. You can check that on your own. And then 25 has an antiderivative of 25t. And then don't forget we have that plus c. Alright, and in keeping with Sal's style, I've ran out of space, so I'm going to have to go up here to find how far I've traveled in those 10 seconds. Now, it turns out I don't need to solve for c. Change in distance traveled doesn't depend on the actual value of the function. Instead, it depends on the difference between values. I want to know the difference between how far I've traveled after 10 seconds and how far I've traveled to begin with. I mean, maybe this was just part of a trip. Maybe I've already traveled 20 miles by the time I start this little 10-second spurt here. Okay. But it turns out it doesn't matter. If we subtract these, let's see, what do we get? I plug 10 into here, and I get a negative 1/3 times 25 cubed, so that'll actually be negative 125 over 3, and that's pretty ugly, so I'm going to put the 3 over so it looks better under the 125. So I plugged 10 into here, and then if I plug 10 in there, I get plus 250 plus c, and we're going to subtract what I get when I plug in 0. Now this term goes away when I plug in 0, but this one doesn't. I get negative 5 cubed. Okay, that gives me indeed negative 125. Paired with this negative, I get positive 125 over 3. And again, plugging in 0 for t gives me 0, so I just need the plus c part. Okay. And my total change, let's see, is I got negative 125 over 3 minus 125 over 3. That's going to be 2 of those, so it's negative, I'll double the top, negative 250 over 3 plus 250. Okay, now to figure out if that's reasonable, I'm going to plug it in my calculator, and I get 250 minus 250 divided by 3. It's about 167. And what kind of units would this have on it? Well, what we did was we computed how far I traveled. So that's going to be 167 feet. Okay, so what was our process here? Our process was to find the distance traveled. We took the antiderivative of velocity to give us a distance function. That was right here. And then we subtracted values of the distance function to see how much the distance traveled changed, to see how far we traveled in that particular time frame. Written as a definite integral, this would be, let's see, where do I have space? Here I have some space. It would be the integral from time 0 to time 10 of our velocity function. Negative t minus 5 squared plus 25 dt. And I don't really have room for the parentheses, and it turns out this isn't necessarily incorrect without the parentheses. The dt is telling you that the integral ends, but I find the parentheses a little bit cleaner when there is room for them. So this time we computed the definite integral from 0 to 10 of this velocity function. Okay, so that's a little bit of an intuitive feel for what a definite integral is. What we still haven't talked about is where in the world this symbolism comes from. Why do I have this elongated s out here? And why do I have this dt over here? We've seen that the dt helps us out in terms of u substitution. If we use the Leibniz notation, then the d whatevers, d variables will cancel. But we'll see later when we deal with Riemann sums where this notation comes from. For now, I just wanted to give you an introduction to the definite integral in terms of giving you the amount of change. If you integrate a rate of change, that gives you the total change. Okay, so I will see you in class on Tuesday.